So in this lecture, we will learn about bivariate normal random variables and understand the last particular discussion of it, of understanding the joint PDF for bivariate normal random variables. We've already seen till now that if x and y are bivariate normal, that means any linear combination of them is normally distributed. So that's the definition of being bivariate normal. So I've let it out in a type form. So a pair of random variables xy is called bivariate normal if ax plus by is a normal random variable for all real numbers a and b. So in this lecture, we will try to understand how the joint density of bivariate normal random variables look like. So I don't know if you recall, we already seen before that if I give you the mean, the variance and the covariance of bivariate normal random variables, like this, if I know the mean of the two random variables, I know the covariance, and the fifth quantity, the covariance, then that determines the entire distribution of bivariate normal random variables. So I had shown a theorem last time that if the variance, covariance, and the means agree, then the two bivariate normal random variables have the same distribution. So in this, what we will do is we will assume one interesting fact that, which you may not understand why. In a second, in the proof, it will be clear why. That if the correlation coefficient is not equal to 1, that is, if they're not perfectly correlated, the two random variables, then the joint density is given by this expression 6.4.2. Okay. That's the aim of this lecture, to show this. It's kind of a hard result to show, and it's a long calculation, so I'll split it up into two lectures. So the first lecture will be just trying to do a key step, or assuming a key step to show the density, and then the next lecture will try to show that key step. But before that, let's just try to understand the intuition of this bivariate non-random variables. So we've already seen that if you recall, if ax plus by is normal, I can take b to be 0 and a to be 1, then I'll get x. And if I take a to be 0 and b to be 1, I'll get y. So individually, they are both normal. That we already established from the definition. But if you stare at the density a little bit, you look at the first term, that looks like a normal with mean mu1 and variance sigma 1. And second term looks like the same thing that would come in a normal random variable with mean mu2 and variance sigma 2 squared. And this kind of represents how they're dependent in some sense. If they're independent, then rho is 0 and you only get these two facts, which is what you expect. So let me try and now show you some how the density would look like. So let me just try it. I have a simulation of it. It's there in my book as well. So let's make it a little bigger so you can see the whole thing. So you see, if you stare at this formula, that these are going to sort of be highest when these guys are going to be 0 in some sense. That is, when at this mu1 equal to mu2, at these points are where the peak happens. And for various sigma 1 and sigma 2, the slopes are different. How they go down is different. Right? Below are the contour plots. So it's largest in the inside, and the next is little 0.1, and so on and so forth. That's how the level sets grow. So the value of the function is really, really small here and very, very large here. That's what this thing tells you. That's some intuition about how the density looks like. It's like an exponential function. It's a bivariate plot on both sides together. Okay. So now let's try and show how to prove this. So like I said, I will assume a key step 1, and then once assuming the key step, I'll try and finish the proof. Okay. So here's the first key step. Okay. So the first key step is the following: that you have to get across that there is two independent normal random variables, z1 and z2, such that probability of y less than or equal to a and less than or equal to b is given by this expression right here. Okay, so this should be for any a and b in R. So let's say for any a and b in R, for a and b in R, this is true. That is, the joint distribution function of x and y, of y1, y2, is given by this. Let me change the color to white so it's all consistent. So remember what y1, y2 were. y1, y2 were the random variables which we assume to be bivariate normal, right, with these corresponding means. Okay. So what I'll do is I'll construct two random variables, z1, z2, which are independent, such that probability of y less than equal to a, y2 less than equal to b is given by this expression where *1 and *2 and *3 are these numbers right here. Okay, that's the aim. Okay, let's try and finish the proof, assuming the claim. Okay, let's assume the key step. Okay, so let's try and assume the claim. So let's try and assume key step. So let's say assume key step. And let's try and finish the proof. Okay. So what will you do? You will know now that probability that y1 less than equal to a and y2 less than equal to b is equal to, so I have this expression right here. Let me copy this down. Probability of this and this, let's copy this down. Let's put this right here, is equal to this. Right, but now of course I know what *1, *2 are also. So let me write those things down as well, so that it's clear for us how to do this. So let's see what *1 is. So *1 is a1 minus mu1. Let's copy that. So I'll paste this right here. *1 is this. What is *2? *2 is this. I'll paste that right here. And *3 is this, right? So I'll paste *3 also right here. What's happened to my thing? Okay, let me try and see. Okay, very good. Copy this and then bring it down here as well. Right? Very good. So now what I'll do is I'll just erase out the *1, *2. So I'll just put the *1s here. So probability of y1 less than equal to a is the same as probability z1 less than equal to this, and z2 less than equal to this minus this, right? So it's this minus, so b1, this quantity minus this quantity right here. So this is an expression, exact expression for probability of y1 less than equal to a and less than equal to y2 less than equal to b. So assuming key step, so there is z1 and z2 independent normal 0, 1 random variables, right? Such that this happens. Right. Once we're here, the proof is almost there. It's not a problem. It's quite close by. So let's try and finish the proof, assuming this, right? So what happens now? This is equal to this. So this is the same as. So now, if you look carefully, this is minus infinity. Okay, so I have dz1 on the outside and dz2 on the inside, let's say. So minus infinity to the limit is a minus mu1 by sigma 1. That's how z1 goes to. And then on the inside, I have a z2 integral. So let me write down z2 integral. So minus infinity. And where does z2 go to? Z2 go to this whole thing until z1, right? So copy, let's put there. Paste it here, make it a little smaller. So it goes to this limit until z1. So let me make it look a little different. So let me call this a little z1. Okay. So little z1 goes to little z1. And the inside is, so maybe I'll make this white so it's consistent. White, and the inside is going to be, let me call this f at the point z1 and z2, and I'll have dz2 inside. Right? This is how it's going to look like. But what is this quantity right here? This quantity right here is the joint PDF of z1 and z2. I should say capital Z1 and Z2. So it represents the random variables. Very good. Now all I have to do is now understand how to compute this expression. So ultimately what I'm trying to do, I'm trying to get to this formula, right? I'm trying to get this formula. This is what I'm trying to get at, right? That's what I'm trying to get at, right? So now let's come down here. So we are here right now. But what do we know about Z1, Z2? They are Z1, Z2 are independent, right? Z1 and Z2 are independent and normal 0, 1 random variables, right? So we know how to do this. So what we do is we can replace this joint density, the very important fact we've learned before, right? That, so I have this expression right here. So I have to find out what f of Z1, Z2 is. So I know this, right? Because they're independent, the key fact we know. F of Z1, Z2 is the same as F of Z1 at the point Z1 times F of Z2 at the point Z2, right? So I'm using the fact they're independent very crucially, right? So this is how I'm using it here. So let me put the normal right here. Let me close this. So here I'm using the fact crucially that the fact is that they are normal random variables. So let me color them a little differently so it's clear. The reason is clear that this is the reason for which they're normal. Here, the reason why they're split up is they're independent, right? And then I know that they are normal random variables. So that means I know the density. I know the density of each of them. So let me just move across. So the equality is clear. And this guy is going to be equal to what now? This guy is going to be equal to e to the minus z1 squared by 2. That's f of z1 by root 2 pi. And it's going to be e to the minus z2 squared by 2 by root 2 pi. Right? So here what I did, I used the fact that they're normal random variables. Right? So let me write this down. Let me take this away because the fact that they're normal. Cut it here. Let me paste it here. A little smaller. Not very small. Very nice. Let me color it as well in orange. So that's what I used it. Right? To get this expression. So now I have an expression for f of z1, z2. Right? So what I'll do now is I will now replace this expression right here. So I'll just erase this guy. I'll erase this guy for you, right? The joint density, and I'll move this across to the side, and I'll just put this round right here. Copy. Very cool. Of course, Z1 was in pink, so I'll call this in pink. That's what I have, right? Very nice. So it's quite a nice idea, quite a nice thing to do, right? So let's try and evaluate the inside integral. Okay, in a little clever way. So let's try and evaluate only the inside integral. Okay, let's inside integral. So how do I evaluate that? So now in the inside one, I just do a simple change of variable, right? So I'll do a u substitution. I will call my z2 by a different random variable name. Let me just do that in a second. So what I will do is I will take my random variable. I'll do u substitution in the second inside one. So in the pink one, I'll do a u substitution. So again, it's a little technical, so you must bear with me. It will take some effort to follow this. But you can look at the book. The book has it clear. So what I'll do is I will let z2, I will change a variable. I will take this whole thing. So what I will do is I will call this whole thing here. I'll take this guy. Okay. I'll place it here. Okay. Of course, I have to remove the integrals now. Remove this integral. I'll place it here. And then what I'll do is I'll just change my b to a y2. Okay. So z2 is going to be equal to this. Okay. So what this implies what now? That's change a variable. So z1 is constant. So fix a z1. Right? Z1 is fixed. So then that means what? That means dz2, write it down, dz2 is equal to dy2 divided by sigma 2 times root 1 minus rho square. That's what's going to be right. So again, rho is not equal to 1, so all these are well defined. So let me make this in pink so that is clear what's going on. And make this in orange so that's available. Very nice. So that means what? The inside integral will change, right? So let's write the outside one. This is equal to. So we think about it a little cleverly that this whole thing, I'll copy it here, right? I'll bring it here. So let me move this across a little bit outside so that I have more space here. So now if you notice, the outside guy is outside here. If you notice, I'm doing substitution, right? So I'm doing z2 is equal to y2 minus this. So when z2 is equal to this, y2 is going to be only b, right? So that's first thing you do. So you put a y2 here, put a y2 here, y2, I'm going to substitute by y2, right? And then, okay, before I do this, get a little complicated. This doesn't depend on Z2 at all. So I can just pull it outside the integral. I'll leave it outside here. This, like I said, if I do a substitution, this just becomes a B. Becomes a B. And the inside is the key now. So this guy is going to be, all this remains the same. So let me do this trick. All this remain the same. And all I have to do is change this Z squared by 2, right? So let me call this as 1/2. And what is Z and minus 1/2? And what is Z squared? Z squared is this whole thing. So I'll take this whole thing and place it here. Yeah, place it. So I'll just, this whole thing squared is what I will get. Very cool. Of course, a very, very complicated expression, and it sort of doesn't make sort of sense sometimes, but that's what it is. Right? Now you can do a little bit of jugglery here. Let's just, if you just stare at a little bit, and then you have this change of variable, right? You have this divided by this bottom guy, sigma 2 times rho 1 squared. In the second integral, what you do is you start here, right? So you have to sort of simplify the part here, this B here, right? And make Z1 as A. So what I do is I'll do another U substitution. So here, what I do is I take this, which I want it to be A for my new variable y1. So what I do is I bring it here. Let me delete this. So here I just let my Z1 be equal to y1 by minus mu1 by sigma. That's what I will do here. Okay. So once I do this, then make it straight a little bit. Do this, then I know that dz1 is equal to dy1 by sigma 1. So I get the top integral becomes minus infinity to A. My new number is A. And this person right here comes down, right? And instead of half Z1 squared, I have half so let is this. I'll make it into white, so it's half, and the Z1 squared, I put this guy, y minus blah, and I close it, the whole squared. Then I have this orange term right here. Then I have this entire expression, this whole thing. I'll leave it as it is. Copy, I bring it down. There's one small thing I have to do. I'll make it a little smaller, perhaps. Yeah. And then instead of Z1, I have now Y1. I have Y1, and I have an extra sigma 1 here, right? Because of the derivative right here. Of this person right here, right? Very good. So now, then of course I have this Z1 right here. So let me just make that Z1 also as Y1. So let me just do a little trick for you. Very nice. Make it a little smaller so that you can have space for my Z1. My Z1 now I have to replace it by this quantity right here, right? So I just put a bracket and I put this one right here. Very cool. And I have a whole square. And all this remains the same. Very cool. So now I have converted, I start off with probability y1 less than equal to a, y2 less than equal to b, and I've come all the way to an integral of the form minus infinity to a, something in y1, minus infinity to b, something in y1 and y2. Okay. So now here's a simple exercise that I will not do, but you can verify that this whole thing is same as minus infinity to a, minus infinity to b, Okay, what's inside I'll let you figure out. You do the algebra, dy2, dy1, y1's outside. Sorry, I want to make it white, sorry. dy1. And what's left inside is this portion right here. So I have a copy. I put this person right here. And then I have the same expression right here. I place this person right here. It's a little bit smaller, but that's what I get. And then I get this expression right here, right? This people. This divided by this. Very good. Now this is just algebra right here. It's a simple exercise. So I'll leave exercise right here to show that this person is going to be this. And so I will cheat a little bit. I will give you the answer, and then you can think about how it is the same as this expression right here. So what have I shown? I have shown that, maybe I'll crop it a little bit so that you don't see the exact expression. So it's a simple exercise to show that the top guy is exactly equal to this. That is, this person is exactly, if you do algebra, exactly is the same as this. So that means the joint distribution function is given by an integral of this form. So this is the same as, if you notice, is the same as what I wrote on before, minus infinity to a. So what have we shown? Let me rewrite it properly. What have we shown? We have shown probability that y1 less than equal to a and y2 less than equal to b is given by minus infinity to a light in orange, minus infinity to b of g of y1 and y2, dy2, dy1. This has to be white by my convention, and this has to be pink by my convention, or orange by my convention. So that means we have shown, this implies that G is the PDF of y1, y2. And we're done. So that was the whole proof, but we assumed a key step. The key step we assumed was this person right here, right? That this is this step here. So let me just recap a little bit. Let me just open a thing. Let me just recap a little bit for you. I'll do a double window so you can see both sides. Right. So what did we do today in this two part? We started off with Bivariate random variable, normal random variable, and we had to show that this was a joint density. For that, I assume that this is a key step. That is, you write the normal and joint distribution function as something coming from an independent normal, and independent normal be equal to other one. So it's z1, z2 are being independent normal random variables, with star 1 being this, star 2 being this, star 3. Suppose you assume the key step. Then I said, okay, I start from here. I rewrite the joint distribution like this. But then I use the key fact that the joint density is a product of the marginals, right? And once I have that, I'm in good shape then. The next step is, all I do is I have to do some algebra of a couple of U substitutions, right? One is right here, another one's right here, in both the pink and the white integrals to get my final answer, which I have here. So that means by showing that probability of y1 less than equal to a less than equal to b is equal to this integral, implies that G actually is the density of joint density of y1, y2. Okay, very good. So now the next thing will be to show the key step. So that's the next step, to show the key step that this happens.